More than 12 million non-institutionalized people living with a disability in the United States alone require assistance with one or more activities of daily living. Systems such as the JACO robotic arm can be attached to a motorized wheelchair and augment a person's ability to perform general purpose tasks that they can't complete on their own. The Personal Robotics Laboratory at the University of Washington aims to extend the capabilities of general purpose robots to accomplish even finer grained tasks. Eating free from food is one of the most intricate manipulation tasks that humans perform. To initiate feeding, a person would switch the robotic arm from teleoperation mode to autonomous mode. The meal begins with the robot picking up a custom 3D printed fork that is docked on the wheelchair when not in use. From that point on, ADA can feed someone an entire meal with or without human intervention. The system integrates onboard sensors, electronics, and computation with the arm and wheelchair, enabling ADA to travel with the person. Robot-assisted feeding requires robust, non-prehensile manipulation of a deformable target that is hard to model. Humans adapt their approach to accommodate the shape and compliance of each forkful of food. Our lab designed ADA to follow a similar approach, using a combination of sensing, perception, planning, and control to successfully acquire and transfer various food items. The camera and tactile sensor attached to the arm rely on a custom-built perception module to wirelessly communicate multimodal sensing information to the robot. The haptic feedback enables ADA to skewer with appropriate force and confirm the attempt was successful. Autonomous feeding is challenging for robots because it involves the manipulation of deformable food items of various sizes, shapes, textures, and compliance. A robot must solve the problem of both where to skewer and how to skewer each item of food, an act we refer to as bite acquisition. When deciding how to skewer, the robot must learn at what angle to approach the item, how to rotate the fork, and what forces to apply. ADA takes all of these factors into account when skewering a piece of food. For each item, whether it is a cube of melon, a whole round strawberry, or a soft slice of banana, the robot determines the appropriate fork orientation and approach angle, then exerts the force required to successfully skewer and lift the item without dropping it. While a piece of melon can be skewered from above and safely lifted off the plate, a soft food like banana requires ADA to approach from an angle that ensures the banana will not slip off the end of the fork in midair. ADA must also determine the best way to deliver the food to the person's mouth, which we refer to as bite transfer. The combination of bite acquisition and bite transfer is straightforward for a compact item with fairly uniform dimensions. But that is not the case with longer items like a spear of celery or a baby carrot. For longer shapes, ADA will spear the item closer to one end rather than in the center. While this is not particularly necessary for successful bite acquisition, the system is also looking ahead to what will make the transfer easy in the next phase. At the point of bite transfer, ADA will position the fork so that the person can accept the food from the opposite end to where it is skewered. This keeps the tines of the fork away from the mouth, which, as we learned from user studies, is important for ease of bite transfer. The system also angles the fork in order to make it easier for the person to take a bite. The arm-mounted camera enables ADA to detect when a person has moved their head during the process of delivering the food item. The robot uses visual servoing to adjust its motion to the user's head movement. This enables it to adjust the path of the fork in midair to reach the person's mouth. When the plate is empty or when the person decides they have had enough to eat, ADA returns the fork to its dock on the wheelchair and the meal cycle is complete. At that point, the user resumes teleoperation until they activate the autonomous mode for their next meal. ADA represents a significant step forward in solving some of the most complex challenges in robot manipulation through a robust system of perception, planning, and control that is informed by multimodal feedback from haptic and vision sensors. With ADA, we have demonstrated the potential for a robot-assisted feeding system to increase independence and improve quality of life for people living with disabilities.